Hi, welcome back to Engineering Dynamics. I'm your host, Dr. Walck, and today I want to talk about planar motion, specifically equations of motion, and why we have so many equations just to talk about forces. And they're actually really important. Think about a toolbox and think about building a house. When you go to build a house, you bring a toolbox and you have lots of different tools. If I want to nail or hammer a nail, I'm not going to use a wrench, right? If I want to sand a wall, I'm not going to use a hammer. You have different tools for different reasons. It makes situations easier. I mean, I could technically bang on a nail with like a wrench, but it's so much easier with a hammer. Okay, so kind of just remember that as we go through developing different types of equations. So if the equations of motion are really broke down into three categories. The first category is your Newton-Euler law, which is going to be the sum of the forces equals ma. That's Newton's second law. And then you also have the angular version of this, which is going to be the sum of the moments equals I alpha. These types of equations of motion, this is best used when the forces aren't a function of anything. So you just have forces and moments. But what happens if you are given a mechanical system that its force depends on position, or its force depends on position, or on velocity, or if it depends on time? This is when other tools become helpful, right? So if I had say my force is some kind of function of time, I'm going to want to pull out impulse and momentum. If my force is a function of position, or maybe like a force is a function of velocity, I'm going to run to work and energy. And I think I want to take time in this video to show you the derivation of each one. And I'm not going to go too far into the derivation, so don't get scared and run away. But I want to explain where A comes from and why we always are analyzing it at the center of mass. And I also want, when you look at work and energy, for rigid bodies in planar motion, you have 1/2 mv squared plus 1/2 I omega squared. And I want you to understand that that v is also velocity of the center of mass. And we know that because of how we derived it and where it came from. So if that interests you, stick around. All right, so why don't we first look over our Newton-Euler. So our Newton and then our Euler. Our Newton actually, like, I know that we know the form as the sum of the forces equals ma. Well, let me tell you something. The fastest thing back in Newton's day was a horse, so he didn't really care so much about acceleration. He actually cared more about, he termed it as momentum, which is p, and he said that it equaled mass times velocity. Okay, he said that an object is going to have X amount of momentum based on its mass and its speed. Okay, that was really interesting to him. So this was created first to get that, because he also said that momentum of an object's not going to start moving unless something forces it, right? So he said that the external forces is going to equal the change in momentum. So it's going to be the change in the object's speed, right? So if the object is just resting and then an external force comes and pushes it, its speed is going to change, right? It's going to start moving, right? It's not just going to stay still. So, and that force is going to have to matter if it's like a large force or a small force. Say if I only want to move a rock, my force won't be that big because my mass is pretty small, right? And then I can move it. If it's a building, maybe my force I create's not big enough. Also, this is rigid bodies we're talking about, so I can take that m out, and I can say that this is really the derivative of velocity in terms of time. And that's how he came up with F equals ma. Now, this is when dealing with particles, right? This is a very simplified version for you to see where this comes from when we talk about particles. When we transfer this into rigid bodyville, we need to say, okay, well, it's the sum of external forces acting on the entire body. So every single teeny itsy bitsy little particle. So I have to sum up all of those particles. I'm not going to do that. No, it's not happening. So, and apparently other people didn't want to do it either, because they came up with a way to say, well, can't we just use the weighted position equation, or the weighted average position equation, to find the location, so of one point. So look at this rigid body, right? And it has like a ton of points. And in the state that this equation is in right now, it wants me to locate every single particle and sum it up. Again, not doing that. So what we said was, if we use the position, the weighted position, if I said 1 over m equals the sum of mr, right? The mass of that one single particle times the position of that particle. So this is I, and each one of these particles will have like a little teeny I. Oh, I'm so silly. That's not plus. Hold on. So this is going to be divided by m because it's the weighted position, right? This is going to give me the position of just one of these, right? If I can locate the position of the center of mass using this, I get, obviously, the position of the center of mass. Good job, Dr. Walck. Okay, where am I going with this? Well, if I can get the position of this guy, and I can get its velocity, and omega I have here, so this is rg velocity. So I can say that v equals omega cross rg. Again, omega, as you know from a definition of a rigid body, omega is the same for all points on the body. The body has to rotate together, but its velocity is dependent on its position from our inertial reference frame, or about the point of rotation. So this velocity is specific to the position of the center of mass. So this velocity, what I'm going to do is I'm going to plug it in here. So this v is really vg, okay? So if I take the derivative of v with respect to time, I'm going to get a, but really it's a of the center of mass, okay? So in planar motion, I really want you guys to understand that when we use the sum of the forces equals ma, it's really ma of the center of mass. And when you break this up into components, and it's like sum of the forces equals ma, sum of the forces in the x direction equals ma, it's still the center of mass, it's in the x direction though. And the same for the sum of the forces in the y, it will equal ma, sum of the sum of the masses times the acceleration of the center of mass in the y direction. My goodness. Okay, so that takes care of Newton's law. Okay, so that's your first equation of motion. This equation of motion also has an angular version. So Newton termed linear momentum with p. So our linear, so I can say, just for notes, I can say that my linear momentum is p equals mv. And Euler said, well, we can do the same thing with angular. I'm going to call it h, because why not, is equal to I omega. Okay, so I'm saying that the angular momentum of an object is going to depend on its distribution of mass, right, and its angular velocity. Because if I rotate an object this way versus an object this way, it will end up being different, right? Its motion profile will be different. And I think you can see that clearly. So what he said was that force, in this case, it's going to be a moment, right, because it's rotation, that the external moments is going to be equal to the change in momentum, right? So again, if an object is sitting still, a person is going to have to create a moment in order for the object to start rotating. And the object, the rotation of it is going to be the change in the rate of its speed. Okay, so if it starts from rest and then you change it, okay, so here it's going to be equal to the change in I omega dt. For planar rigid bodies, we can pull that I out, and it would be the change in angular momentum. In this case, it would be the change in omega. So m is then equal to I alpha. Okay. The same. So for this, I here is going to be I of the center of mass. And that's because it's going to be, remember, it is the angular version of this. So if this is the center of mass, this is also going to be the center of mass. Okay, so just know that this is assumed to be about it. It doesn't have to be, but if you choose, it just has to be about the same axes that the m is taken. So if you're doing the moments about the center of mass, I has to be about the moment of center of mass. If you're taking moments about some random point, you will then have to do I about some random point. So to do that, you'll have to use your parallel axis theorem. That should be like a totally different lecture. But basically, if you want I across, like taken about some random point, you're going to do I of the center of mass plus md squared. Okay, and the d is the distance between the two axes. So the parallel, the axes that's going about the center of mass, which is I, and you are going to transfer that about another parallel axis, right? So that's the distance between the two axes. Okay, so that's Euler. Now, so now you automatically have two moment of equations. I really just count them as one, but whatever. We have the sum of the forces. Oh my goodness, I can already see this video is going to be terrible. Okay, so we have the sum of the forces equals ma, and we have the angular version, which is going to be the sum of the moments equals I alpha. Now I want to, because so that was, if we look up here, we said that we have this one. What happens if it was given to us as a function of time? Why don't we go through that? So how did we get impulse and momentum, or how do we deal with forces that are functions of time? Well, why don't we go back to our original F equals ma? And we kind of already did this, because remember up here where I said that the linear momentum is mass times velocity? Okay, well, and then I said that F is the change in momentum, in linear momentum. Okay, why don't we go from first P is equal to mv, okay, and then we said that F is equal to the sum of the forces is equal to the change in P over T, right? What if we rearrange these variables? If we get the sum of the forces is equal to Ft dp, now we can work with forces as a function of time. And this here is actually termed impulse. That's all it is impulse. And then on this side, we just have the change in momentum. Okay, so this is going to be the change in linear momentum. I don't even know That doesn't even look like a U. Okay, that's the change in linear momentum. Okay, so this is the impulse portion of it. When we talk about impulse, I think a lot of textbooks will call this J. And why don't we just try to understand for a minute what does this mean? What does the change in P equals J mean? Basically what this means is it's saying when you have a change in momentum, you will have an impulse of some kind. If there is no impulse, then momentum isn't going to change. That's based off of Newton's first law, okay? Lastly, I want you to notice if there is an impulse, that means that the object will either speed up, it's going to slow down, or it's going to change directions, okay? That is going to be your second tool, okay? A few helpful, two other like versions of this. Remember that J equals, because when we say change of P, we have the linear version. You can have change in velocity, but you also have an angular impulse, which would be I change in omega. Careful here that you cannot add these together. They are separate. So you might want to put a subscript here that says that that's linear and that's angular. So if you have a problem that says, yeah, what is the impulse of this system? You would have to answer with the system has a linear impulse of and an angular impulse of, okay? So when we are given forces in terms of time, you are going to run here, okay? Before we move on, let's just look at what type of problem that you would use, or that you would be asked to use this type of equation of motion. Take a look at this. What if I said, okay, so we have a rigid body sliding and rotating. A 2 kilogram rigid bar of length 1 meter slides along a horizontal surface while simultaneously rotating about one end at 3 radians per second. Calculate the impulse required to stop its motion in 2 seconds. Okay, so it's saying what type of impulse, what would you have to do to stop this from rotating any further after 2 seconds? So basically I have this, it's in a horizontal plane, which means we don't care about gravity. We do have a collar on it, but the collar is really not doing anything. So basically you're just looking at something doing this. So how would I go about solving that when it comes to impulse? I'm going to go ahead and describe our linear. I'll work with that first. It states that J linear is equal to mass times velocity, the change in velocity. So my mass, it said, was the bar was 2 kilograms. Yep, the rigid bar was 2 kilograms, so I have 2 there. It also stated that it started from rest and that it had a final velocity of 1.5. So this gives me -3 Newton per second. So it has a linear impulse of -3. So we have an angular momentum of -3. Remember, it's asking for force though. So we need to find force. And we said that force, the sum of the forces, is going to be the change in the change in impulse. And we also separated our variables to do that. So now I can state, if I rearrange this equation a little bit, I can say that the force, or the average force in this case, is equal to -3 divided by time, the change in time. It started from rest and it wants to go to 2 seconds. So here it's going to be an average force to stop this thing at 1.5 newtons. So literally we have a force that you would have to counteract. It would have to be a linear force of 1.5. What about the angular component? Okay, so we have an angular component here of mass change in, oh, it won't be mass, my goodness. Why can't it be mass? Well, because angular, the mass distribution is going to matter now. So now we have I change in omega. So this is going to equal I is, did they give us I before I calculate it? They didn't give us I, but we do know that I is rotating about its, about the end. And they do give us the length of the bar. So it would be 1/3 ml squared, change in omega. So it would be 1/3, the mass they said was 2, and the length is 1 squared, change in omega. So this is going to just be 2/3. And my change in omega, we're going to go from rest to, it said rest to oopsies, 0 to 3 radians per second. So this is going to equal -2 Newton meter second. Notice that the difference here, okay? So now I can say, okay, well, now I can say that the sum of the moments, a lot of times when we talk about momentum and impulse, sometimes people use torque, so you could also use the average torque here, but that is just going to equal the angular impulse divided by the time, okay? Because remember, we started with Newton's law equals is the change in linear momentum over time, and then we did this. It would be the same for moment, which would be the change in angular momentum over time, and you bring that time over, okay? So if I'm looking for the moment that it requires, then I would do -2 Newton meter second divided by the time it took, and I think it was asking for 2 seconds. So this would equal 1 Newton meter. Okay, so that's like a kind of a simple example. I'm sure I'll do another video with more. So let's look at our last equation of motion, where we have work and energy. So right now you have here, actually, let me look it up here. So we just did this one. So we had that J linear is equal to mv, and J angular is equal to I omega. Okay, so now we have more in our toolbox. Okay, so let's look at our last equation of motion. That's going to be our work and energy. How do we get that? All right, so again, well, you have to start with Newton's law, okay? And work and energy, think about the definition. Work is some amount of force that is required to move an object, okay? So if we're talking about work is some sort of force to move an object, I want to introduce that movement. That movement is some kind of displacement, right? So I want to introduce a parameter of displacement. So I want, the first thing I'm going to do is dot this with dx and take the integral. So I'm going to integrate both sides and dot it with dx is going to equal m. And I took the m out just because m is constant, right? And then I'm going to dot it with dx, okay? So this integral would be from x1 to x2, and the same with this force. This is the definition of work, okay? I want to focus right now on this side, okay? So this side, the next step that I'm going to do, this A and this X are vectors because this is acceleration and displacement. So what I want to do is I want to separate its components. So I'm going to say AX dx plus AY dy plus dy plus AZ dz. Okay, and then I want to turn my attention to this. Okay, I'm basically asking you to take the integral of this. Can I take the integral of this? Well, when we integrate, we do it with respect to time, and this is respect to distance. So I can't. I have to use the chain rule. So if I recall, a is equal to dv dt. To get acceleration in terms of position, I have to use the chain rule. So I'm going to do dx dx. What is dx dt? It's velocity. So this is really equal to velocity times dv dx. So in place of x, I can substitute this in. Okay, so why don't we do that? So if I put m, if I'm just looking at the first term, I have v dv dx times dx. Well, now my dx cancels. So I'm left with a beautiful dv dv equation. So why don't I fully substitute the dv in, the v dv in? So I have mass, and then I have the integral, I have ax. If I'm looking at the component a, the x component, I have to do the same for velocity, because remember that velocity is a vector, so it has its components too. So I want to break that velocity up into components. So it's going to be vx dv plus vy, excuse me, plus vy dv plus vz dv. Okay, looking again at this first component, why don't we just go ahead and take the integral? And this integral is going from v initial to v final. What's the integral of v in terms of v? It's v squared over 2. And then it's evaluated from vi to v final. If I plug this in, I'm going to get v final squared minus v initial squared divided by 2. Or I can say each one is divided by 2, like that. Okay, so why don't I then plug this back in for each one? So my equation becomes m, I have vx final minus vx initial squared divided by 2 plus vy final minus vy initial divided by 2, and these are squared, plus vz final squared minus vz initial squared divided by 2. In the next step, I want to group all of the finals and then all of the initials. So this is going to become m. I have vx final squared plus vy final squared plus vz final squared, and all of that would be divided by 2 minus m, and then I'll have all of my initial terms, plus vy initial squared plus vz initial squared. All that will be divided by 2. Now take a look at this. What is a x component squared, y component squared, z component squared? It's a resultant vector. We also can say that it's Pythagorean theorem. So v equals the square root of vx squared plus vy squared plus vz squared. If I take the square root and I square both sides, right, that square root is going to go away. It's going to go away. Okay, so really I can replace this whole thing with just a vector v final. So I can say that this is m v final squared divided by 2 minus m v initial squared divided by 2. And we know that kinetic energy is 1/2 mv squared. So this is a change in kinetic energy. So if we go back up here, we stated, let's lasso this guy, and let's move him down. So you can see that work, that the external work, so this is work, remember, is equal to the change in kinetic energy. Okay, but if you notice here, the kinetic energy that we just derived is only linear. And that's okay for particles because particles only have linear motion. It's not okay for rigid bodies. Rigid bodies can rotate and rotation matters. So we're going to need to come up with the second portion of kinetic energy because kinetic energy is equal to the linear portion plus the angular portion. Okay, so I need to talk about where that comes from. Now, I'm not going to derive it because really it's going to be going through the same steps. You are going to start with Newton's second law and recall that A is really of G when we're talking about rigid bodies. We discussed that before. We also want to be careful and recall that this V is V of the center of mass. We know that because we took, if you go back here, we took the sum of the forces equals A. We know that's AG. We know that because all the way up in the very beginning, we did the weighted position equation. So just from all of that, because we used that one time, we have to make sure we carry it all the way through. So in work and energy in the linear portion of it, that V is V of the center of mass. This one here is I omega. So instead of dotting this with dx and taking its integral, you can dot it with d theta. And you would also represent V as omega cross R. Okay, I'm not going to go through that derivation though, but it's basically the same thing. And what you are going to do is you are going to represent, if a problem has forces in terms of position or velocity, you're going to run here. So why don't we take a moment and look at that same example. So, but this time, instead of calculating impulse, I want to go ahead and calculate kinetic energy. So we still have the same system. You have this 2 kilogram rigid bar, has a length of 1. It slides on a smooth horizontal surface while simultaneously rotating about one end at 3 radians per second. So I want to calculate the total kinetic energy of the bar. So our kinetic energy we have is going to be this, right? Plus 1/2 I omega squared. We know that the mass of the object is 2 kilograms, and we know that omega is going to be 3 radians per second. We also know a little bit about I because just like before, it's rotating about the end, so that's 1/3 mass times length squared. And then this velocity. Here, velocity equals, because it's in pure rotation about that point, velocity equals r omega. R is so we had this is our diagram here. Remember that this V is Vg. So I want the velocity located here. So that means that my R is going to be the distance between the point of interest and the point of rotation. So the velocity, the R that I'm going to use here is 0.5, not 1. Okay, be very careful on that. Okay, so my equation then becomes 1/2 2.5, omega is 3 squared, plus 1/2, 1/3, m is 2, length is 1 squared, omega is 3 squared. I should get a change in kinetic energy that is equal to 5.25 joules. So that's a very simple problem. I want you to go ahead and take a look because we haven't said anything about potential energy. So potential energy shows its face on this side of the equation. Just like when we talked about impulse and momentum, we said that, so we ended up saying that our linear impulse is equal to our change in momentum, linear momentum, which is V, to our linear momentum. And we also said that our angular impulse is equal to our change in angular momentum. Okay, so we have this side and this side, and then we also have that impulse. Impulse, remember, is F dt. Okay, on work and energy, we have that force is a function of distance, and it is going to be equal to the change in kinetic energy. But it could also be a change equal to potential energy, okay? And the potential energy is going to really come from this side of the equation, okay? So we have, so what are some potential energy examples? We have spring, right? Spring is definitely in terms of position, right? Because its force will change depending on the distance that it's acting. So that would show here, it would be force of a spring times the distance that it's, stretching. We also have weight. That's definitely position related, because it's like the change in height and the change in stretch. And then you also have like a friction force. That's non-conservative though. So now I'm hoping that the way I'm doing it, it's making sense. So that's pretty much all the equations of motion, actually. I would like to put them all together in one nice slide real quick. So in the beginning, we said that we had equations of motion, right? And we said that sometimes we just have forces and we have moments. They're not a function of anything. They just simply are. But then sometimes we said, well, we could have forces in terms of time, and we could have forces in terms of position, or forces in terms of velocity. If I have a problem, so say you're looking at a problem, the first questions that you should ask yourself is, how many rigid bodies are there? Okay, say there's two. So you're going to draw two free body diagrams. After you're done drawing the free body diagrams, you're going to ask yourself, are there forces involved? If you say yes, you are going to then ask yourself, are the forces a function of anything? If your answer is no, then you know that you can reach for Newton-Euler. Newton-Euler is going to be F equals ma, and m moment or torque equals I alpha. If you answered that question by saying I have force in terms of time, then you are going to say, oh, I have impulse and momentum, which looks like F dt equals impulse and momentum. So this would be the linear, which would be m change in linear momentum. And you would also have an impulse equals the change in angular momentum. So here again we have impulse. This is your linear impulse. This is your angular impulse. This is your linear momentum. And your angular momentum. What if you answered your question by saying my force is a function of position? Well, now you have work. So now you have force in terms of displacement, because work is how much energy does it take to move an object, right? So we have force dx. This is going to equal the change in kinetic energy, or you can say 1/2 mv squared plus 1/2 I omega squared. Again, this is going to be your potential energy side, and this will be your kinetic energy side. I think that's everything. I hope that this video helped you, and I'm sure I'm going to post a video of some examples. If that interests you, the examples part, comment below, and I will try to get it out right away. Okay, thank you so much, and I will see you in my next video.